I'm Bobby Kubor, a Digital Innovation Solutions Architect at AWS. I think it's fair to say that the past 12 months have been quite difficult for everyone. Not just in Australia, but especially in other parts of the world where COVID-19 has impacted every facet of life. As a technologist myself, I do see a slight silver lining, which can be effectively summed up by the saying that there are decades where nothing happens, and then there are weeks where decades happen. Over the past 12 months, we've seen private and public institutions work together to create a vaccine in a fraction of the time previously thought possible. We've seen technology advancements that allow us to more effectively work and collaborate from home. We've seen the use of autonomous robots for unsafe tasks, especially over the past 12 months, such as the disinfection of hospitals. And finally, we've seen technology enthusiasts come to the support of their fellow citizens, helping 3D print masks and respirators to keep frontline healthcare workers safe, as well as build autonomous systems to safely deliver supplies to those in lockdown. This last example is what interests me the most, because as a tech enthusiast and someone whose job it is to encourage experimentation for the purpose of innovation, it's not until recently that I've had access to this sort of impactful technology. Over 10 years ago, that sort of technology was way too expensive for me to even consider purchasing, and to make matters worse, I wasn't even sure I'd be able to build anything. I'd never really built anything in the robotics space before, and I had no theoretical background. Would I just be setting money on fire by purchasing hardware I probably couldn't use? If we fast forward to today, we're seeing a much more even playing field when it comes to technology. The pay-as-you-go mechanisms that the cloud provides, as well as the ability to experiment with very little risk, has put technology, such as machine learning and robotics, right at our fingertips as tech enthusiasts. What I'm keen to do in this session today is really to peel back the covers on a previously considered niche topic, such as robotic development, and provide an understanding of how and why it's become so accessible, and then give you a blueprint on how to get started. The easiest way to illustrate this is to focus on a specific problem that I think can be solved with autonomous systems, and that I also think fellow tech enthusiasts would appreciate. Around this time last year, like many of you, I was getting frustrated with toilet paper shortages. I found myself driving from store to store, looking at empty shelves, while being fully conscious of the impact it was having on my ability to socially distance. I wondered how robotics could potentially solve this problem, so I started building a bit of a fun prototype.
Alexa, can you get me some toilet paper from the local shops?
Leave it to me. Deploying autonomous toilet paper finder now.
So what you can see here is a robot that I've created called TPBot. I've requested toilet paper from Alexa, who's acknowledged my request, and sent TPBot out in search of toilet paper while I effectively remain COVID safe at home, waiting for TPBot to return with the precious cargo. Now, TPBot is what's commonly referred to in robotics as a mobile manipulator. That is, that it has a mobile base it uses to navigate to a specific location, and it has a manipulator or a robot arm mounted on top that allows it to manipulate the environment around it. As you can see, TPBot has navigated to the toilet paper roll, it's identified it successfully, it's grasped it, and it's now carrying it away. For most people, this problem may seem quite trivial, but that's probably because as humans, we take the level of effort involved in grasping an object for granted. So if you think about what's involved, there are a number of different subtasks that need to be built. From a robotics perspective, you need to understand the verbal request provided, which in this case is to collect toilet paper. You then need to visually recognize the toilet paper and then navigate to it, positioning yourself at the right distance and angle. You then need to set the joint angles in the robotic arm correctly to reach out and grasp it. And then finally, once you do grasp it, you need to ensure your grasp is not too soft or tight, and you need to bring it back without colliding with anything. Now that's a fair few things that you need to take into consideration when building a robotic device such as this. But thankfully, this sort of build is considerably easier using the AWS RoboMaker service. Now, before we even look at these components in detail, we first need to decide the development framework we're going to use. The AWS RoboMaker service provides a development environment for developers to quickly and efficiently build robotic applications using the Robot Operating System, also known as ROS. ROS was founded in Stanford Labs over 10 years ago and is now managed by the Open Source Robotics Foundation. While it's commonly and understandably confused with an operating system, ROS is not actually an operating system. It's a development framework, an ecosystem that includes robotic development tools and a simulation engine, also known as Gazebo. Its popularity is growing significantly, primarily because it moves away from proprietary software control systems that are really built to fulfill a specific task. This would obviously cause long development times because robotic developers essentially had to reinvent the wheel with each new product. What ROS does is that it standardizes and open sources a lot of robotic development to allow reuse, which then facilitates and encourages the sharing of good ideas. If we dive a bit deeper into the ROS development framework, the best way to explain it is the connecting of nodes that are effectively bits of software written in Python or C++ that take care of a small subset of tasks, such as controlling an actuator or reading a sensor. These nodes are then able to communicate with each other using a publisher-subscriber protocol. So if we consider TPBot, there may be a scenario where someone's controlling it with a remote control. That remote control could be represented by the TP teleop node on the left-hand side of this diagram, and it may send communication to the node which is responsible for movement of TPBot, which is represented by TP pose on the right side of the diagram. In the event that a user presses the up joystick on the controller, that information would be published to the command velocity topic in the middle of this diagram, which would then be sent to the pose node, which is subscribed to the topic to move TPBot accordingly. So now that we've got a bit of an understanding regarding the high-level development approach to build TPBot, let's take a look at the verbal invocation that was used to send TPBot on its way. As you would have noticed, I was speaking to an Amazon Alexa device to take my request and pass it on to the robot. Technically, we could take the Alexa chatbot used and integrate it directly into the robotic device using an AWS service called Amazon Lex, which would allow us to take the Alexa conversational engine and place it into any device that we like. Unfortunately, TPBot doesn't have speakers or a microphone, so we've had to augment the solution with an Amazon Echo Dot device. Once we've provided Alexa with our request, Alexa then sends that information to AWS Lambda, which is a serverless compute platform that allows us to execute code based on an event and only pay for the time it takes to execute. This is considerably more cost-effective and efficient than running the code indefinitely on a server, as is done traditionally. Finally, our code in Lambda determines we want toilet paper and sends that information to the robotic device using the AWS IoT service. So if we take a closer look at the Alexa chatbot, you can see why these devices have become so popular. The technology has democratized natural language understanding and processing by abstracting away the complexity of machine learning and allowing you to simply specify 4 parameters. The first parameter is an intent, which is a representation of an action that the robot wants to perform. So in this case, it's to get toilet paper. However, we could potentially add another intent later to get pasta, considering that was also in high demand at the time. The next is a sample utterance, which is how a user might convey the intent. So in this case, we're saying, hey, get me some TP. One thing to note here is that the sample utterance doesn't necessarily need to be word for word. Alexa will take care of slight variations. In our case, we need to also understand how many ply is required. Otherwise, TPBot could disappoint us with single ply toilet paper. So we've specified that TPBot requests this information if it isn't already provided in the sample utterance in the form of the question, how many ply? When this is provided, such as replying with 3 ply please, the 3 is stored in a slot, which is a variable that we then need to act on. We pass this variable to fulfillment, which is the Lambda function that is used to notify the robot of our request for 3 ply toilet paper via the AWS IoT service. Okay, so we've worked out how we're going to invoke TPBot. Assuming that we use GPS to navigate to the local shopping center, how does the robot actually navigate inside of the shopping center? There's no GPS, so how is it going to find its way around? Well, there are 2 primary methods for robotic navigation. One, which is used more in controlled environments by what are called automated guided vehicles, where robotic devices follow a predetermined path using physical guidance mechanisms. You often see these robots being used in more static environments such as factories and fulfillment centers, which hardly ever change. This obviously isn't going to work for our use case, as we're probably going to need to dodge pedestrians or even other robots also looking for toilet paper. What we need is a more dynamic navigation capability, used by what are called autonomous mobile robots, or AMRs. These robots are able to use an internal map to calculate the optimal path to a destination and modify plans quickly if obstacles are encountered. The way that this technology works is by using a navigation capability called simultaneous localization and mapping, also known as SLAM. It works by first creating a map using a process called G-mapping. This is where an operator is manually driving the robot around the environment and using onboard sensors such as LiDAR or depth cameras to create a 2D map of the environment. You can actually see this occurring in this video here, where on the right-hand side we have a simulation environment and we're manually controlling the robot using a controller to move around the building and effectively map it out. You can see the map actually being created on the left-hand side. Now, one thing to note with this process is that instead of driving a robot around a physical location for G-mapping, we could actually take a digital representation of the building in the form of a BIM file and import it into the simulation similar to this example to do the G-mapping process, as opposed to driving the robot around a building in the real world. This makes the G-mapping process considerably easier and is actually what the architectural engineering and construction firm Takanaka do in Japan for their construction-based robots. Once we've created and saved the map, we can then use it to navigate the environment. As you can see here, TPBot is attempting to navigate from one room to the other, which is evident on the left-hand side of this demo by the line drawn through the house indicating the most optimal path. In the simulation on the right-hand side, we're effectively spawning couches where the optimal path is dictated, and you can see the path dynamically change when the robot comes into range with the area and notices the obstacle. As you could imagine, building out this sort of navigation yourself could prove quite difficult. Coming back to the benefits of ROS, the mapping and navigation capability we described here is an open source drop-in capability that anyone can take and use on their robotic devices, which certainly makes robotic development more accessible when you abstract that sort of complexity. So we've got movement and we can navigate to the aisle where the toilet paper is. How do we actually grasp it? Once again, this is where the ROS community comes to the rescue, with more drop-in open source capabilities, this time in the form of another framework called MoveIt, which runs on top of ROS. Once you've specified the joints and range of movement in the robotic arm, the MoveIt framework then provides your robotic arm with the necessary functionality such as motion planning, manipulation, collision checking, as well as movement and kinematics. Robotic arms do seem quite trivial considering we have arms ourselves, but having 6 joints in an arm and trying to think of the exact angle each joint should be to reach an object is really quite difficult. MoveIt can make this considerably easier by being able to leverage what are called inverse kinematic solvers, which are able to calculate the joint angles required based on the coordinates of the desired object in reference to the robot's position. Finally, once we've finished our robotic build, it's time to test. If any of you are application developers, you'd be familiar with essentially going into the brace position the first time you run your code. You know it's extremely unlikely to work. That's why you generally don't deploy and test in production. Why would a robotic application be any different? Deploying to physical hardware could be dangerous and costly if things go wrong, which is why AWS RoboMaker has a hosted simulation environment, also known as Gazebo, which is part of the ROS ecosystem. The simulator is able to replicate things like gravity, friction, shadows, and inertia. It's the perfect place to spawn and test your robotic application. One of the primary benefits to simulating in the cloud is really the elastic factor. Rather than having to move a physical robot from one scenario to another for testing or queuing simulations one after the other on a desktop, you can spawn multiple simulations in parallel in AWS RoboMaker to collect test results much quicker and therefore iterate on development much quicker. This is ideal for things like regression testing, where future enhancements to the robotic device require a fleet of tests to be run to ensure no previous functionality is broken by the new feature. iRobot, who build consumer robots like the Roomba, are a perfect example of this, using AWS RoboMaker to run 5,000 tests in parallel monthly, which allows them to validate robotic software builds in hours instead of weeks, and ensures they're catching defects in development instead of production. So what we're seeing here is TPBot spawned into a simulation. On the right-hand side, you can see TPBot in the simulated world. On the bottom left, you can see the map that it's using for navigation. And on the top left, you can see what the camera mounted on the front of TPBot can see. The first thing TPBot does is position itself appropriately to the left side of the room before approaching the beer can on the stand. Now, I've chosen a beer can because that was the closest thing in terms of dimensions to a toilet paper roll in the open source models that come with the simulation environment. Using this was considerably easier than creating my own custom toilet paper roll model. One thing you'll notice as we approach the can is if you look at the camera view is what looks like a QR code below the can on the stand. This is actually what's called an Aruco marker, which is commonly used in robotics for identification and is admittedly what I'm using to recognize where the toilet paper roll is. The other benefit, without going into too much detail, is that it's able to provide a frame of reference regarding distance or depth using a regular camera. This is critical because we need to know exactly where we are in relation to the can to ensure we can appropriately set the joint angles in the arm. So what you can see now is TPBot reaching out to grasp the can and effectively failing. It overshoots and it didn't even open the gripper. The reason why I wanted to show this is primarily because TPBot is actually slightly tipped forward due to the weight of the robotic arm when it's fully extended. This is one of the key reasons why simulations are so important. If you have a robotic arm transported on the back of a truck, this is the sort of thing you're going to want to avoid and can avoid if you're testing in a simulation first. Once we've ironed out the bugs, it's time to deploy to our army of TPBots that are going to be released throughout the city to find and collect my, by now, much needed toilet paper. This is where RoboMaker's fleet management capability really shines. We're able to specify robotic fleets and deploy to them in a controlled manner. In this example, we're deploying to 10 robots in a fleet, and we're going to configure the maximum concurrent deployments to ensure that we're able to roll out our deployment in a controlled manner. We're also going to set a failure threshold so that if we start to see failures appear, we're able to halt a deployment rollout and prevent potentially bricking an entire fleet. As you can see in this example, we've rolled out to 80% of the fleet, but have halted deployments as we've crossed the failure threshold of 15%, where 20% of the devices so far have failed deployments. One of the other really cool things about AWS RoboMaker Fleet Management is the ability to set a flag on the robot indicating that it's ready to accept deployment. If TPBot was on its way home, for instance, with some toilet paper, and it was crossing the road, the last thing that you would want is for the software deployment to occur mid-operation. This could result in effectively a car smashing into TPBot and smashing it into many pieces, or even someone coming along and stealing the toilet paper while TPBot is going through the software update process. You'd probably want to wait till TPBot is docked before beginning the update process. Now, understandably, most people look at this use case as nothing more than a bit of fun, which is fair. TPBot isn't moving into production anytime soon, so unfortunately, I'll still be collecting my own toilet paper. What most people don't realize, however, is how easily these concepts map over to the real world. This video is from Woodside, who are Australia's largest operator of oil and gas production, and are using the exact same technology specifically for the purpose of operational task autonomy. What you can see here is a robotic demo in what would potentially be an unmanned offshore facility. The hardware that the robot has navigated to has been set up to pump water around and around in a loop, and an error has been purposely introduced to the system, which would usually result in a remote shutdown. In this case, when the remote shutdown conveniently fails, this autonomous robotic device named Ripley can be deployed to manually shut down the water pump itself. Ripley has a mobile base which it's able to use to navigate itself appropriately, and additionally has 2 robot arms for manipulation. Ripley is coordinating a 4-step procedure where no one is required to drive, which involves navigating itself using the same SLAM process we discussed earlier, positioning itself appropriately, and if you look closely, you can actually see the Aruco marker, similar to what we were using with TPBot. It then uses its robotic arms to push the big red button and shut off a number of valves, effectively shutting down the water pump with no human involvement. Interestingly, the movement in the arms was developed by NASA for the Robonaut, which is the robotic astronaut created to work alongside astronauts and perform tasks that require some level of dexterity. So hopefully you can see how this sort of capability can be incredibly useful within small businesses to enterprise. You no longer have to send a human in a chopper to the offshore facility to perform that manual shutdown. You can also see how this sort of capability would be incredibly useful for scenarios that effectively may be too dangerous to send humans into. So hopefully you're wondering how you can potentially get started. Something I'm really excited about is that AWS has been working on building a cloud robotics curriculum, which has been released onto the AWS Educate platform, but it's also available publicly on GitHub. The great thing about this workshop is that it's aligned to a low-cost robotic device if you decide you want to move out of simulations and actually get hands-on with some hardware. We're doing a phased release of the modules, with the first 4 modules currently available to help you get started with robotics. They cover things like the fundamentals of robotics, which introduces you to the basics of robotics with an overview on robot components, modeling, and main problems to solve to achieve a fully autonomous system. The primary learning objectives include insights to understand robotics hardware and software and get you comfortable with working with a robotic system capable of running tasks within a real environment. The second module is getting started with ROS, which walks you through setting up a Linux and robot operating system development environment. The primary learning objective includes getting comfortable with ROS and teaching you the basics of how to control robots. The third module is getting started with AWS, which guides you through setting up the robot development environment in the cloud using AWS RoboMaker. The objectives of this course include understanding the cloud development environment, preparing to write programs for robots in the cloud, and integration with various AWS cloud services. The fourth module is really around ROS 2 and ROS, which will get you started with writing robotic software in the robot operating system. Finally, if what you've heard today has sparked your interests, I'd like to leave you with the following 3 thoughts. The first is to dream big. Have a think about what problems could be solved in your town, city, or country, and what the open source community is working on today. I'm constantly inspired by reading what the community is working on, especially over the past 12 months. The second is to get hands-on. There's no reason for robotic development to be exclusive. It's now completely learnable and accessible. The third is to lean on the open source community to test and build out your ideas quickly. The community is growing rapidly and there's never been a more exciting time to get involved. So have fun building, and thanks for watching. If you enjoyed this session, please leave feedback.